I am going to continue this video series on the sign tests with the third case, making inferences about a median of a single population. This is the sign test for population location, and this is probably the case that the sign test is most famous for. Researchers are often interested in the center of distribution, so let's consider for a moment center of distribution indices. The mean has become the overwhelming choice as an index for the center of a distribution, and it's even used as a representation of that distribution on regular occasions. A strong reason for this is that the powerful method of least squares analysis is based on deviations from the mean. There is no denying the power of least squares analysis, so I understand how the mean has become so popular. But imagine we are not using the method of least squares. Let's compare the two competing center of distribution indices, the mean and the median, and look at some of the properties. Perhaps another reason that the mean is so popular is that it is based on the quantity of each score in a sample. By contrast, the median is based on a collective location of scores. A single score can change, and while it would change the mean, it may not change the median. The mean represents the center of symmetrical distributions. The median represents the center of any unimodal distribution, center or otherwise. It is well known that when we have skewed distributions that we should look at the median rather than the mean, yet the mean continues to reign as the most popular center of distribution index. The mean is influenced by outliers, no matter what the cause of those outliers, error of measurement, error of data entry, or just cases that are unlike the other cases in the data. The median, by contrast, is resistant to outliers. The mean does not exist for some population distributions. The median exists for all population distributions. When you look at these two lists of properties for the mean and the median, I am not surprised if you raise your eyebrow a little bit and say, perhaps we should be using the median more often. Yes, perhaps so. But will use of the median allow us to make inferences about the population center? Indeed it will, as we will now see. First, let's define the population parameter and sample statistic for the median. In a population distribution, we want to find the value at which half of the distribution is beneath that value and half of the distribution is above that value. That is the population median. But of course, in research, we're never going to be able to look at the entire population, so we draw a sample. Once we have a sample of data, the first step is to put the data in a list in ascending order. Once we've done that, if we have an odd number of observations, the sample median can be found by taking the number of observations, n plus 1, dividing by 2, and finding the score that is in that place in the ordered scores. Similarly, if n is even, we have to find two scores. First, we take the number of observations divided by 2 and find the score that is in that place in the list of ordered scores. Then we take the number of observations divided by 2, add 1 to that quantity, and find the score that is in that place in the ordered scores, and then average those two scores, that is, add them up and divide by 2. Let's look at an example. Here are 12 scores that are drawn as a sample from a population. The first thing we have to do, remember, is to put them in order from smallest to largest. Here I've done that. Since there are 12 scores, we have an even number of scores. 12 divided by 2 is 6, so we need to find the sixth score in the ordered list of scores. That would be 107. Then 12 divided by 2, that quantity plus 1, would give us 6 plus 1 or 7, so we find the seventh score in this list, and that is 109. We now average 107 and 109, and we end up with a sample median of 108. The sample median is of course useful as an indication of the center of our sample of scores, and it's also a good guess about the population median, but we cannot attach any probability to that guess, so let's now look at a hypothesis test about the median. As with any hypothesis test, we have conditions for valid inference. Here are the conditions when we use the sign test to conduct a hypothesis test about the median. First, we have an underlying continuous construct of interest. Given the continuous nature of the construct, we typically would measure our participants using quantitative measures, but we could use ordinal measures, such as those you would obtain with a Likert scale. And then we have to have independent observations. If you think for a moment about how this compares to the conditions when we're doing a hypothesis test for the mean, we typically use a one-sample t-test for that hypothesis testing. There is a continuous construct of interest, yes. There is measurement of a participant that is always using quantitative measures, not ordinal. There are independent observations. But there is an even stronger condition, and that condition is that we have normally distributed data. Yes, if the data are not normally distributed, we could take a large enough sample size to be able to rely on the central limit theorem, but that size may be substantially large, especially if our population distribution is far from normal, such as we might get if we have a heavily skewed distribution or a lumpy-bumpy distribution. There are no conditions for valid inference with the sign test that require us to have any particular shape of distribution. The null hypothesis is that the median is equal to some hypothesized median. I'll indicate that as theta sub 0. Now the next step is to make adjustment to our observations. We have an ordered set of observations. Let's call the ith value in the set x sub I. And to adjust these observations, we subtract the hypothesized median from each x sub I to yield y sub I, another ordered set, but now one that has been adjusted based upon what our hypothesized median is. Why do we do this? If our null hypothesis is true, and if we subtract the median from each value of x, then what we end up with is a distribution that is centered around a median of 0. This enables us to use the sign test because the test statistic will be the number of positive values. That is, the number of values in which our adjusted score, y sub I, is greater than 0. As with other times when we have used the sign test, this is the same as conducting a binomial test with the probability of a positive value being 0.50 under the null hypothesis. Here's an example. Let's use for our null hypothesis that theta, the population median, is equal to 100. Let's use as the alternative hypothesis that theta is not equal to 100. In previous videos, I have used one-sided tests because they're consistent with my belief that we should have theory guiding our research and therefore should be anticipating outcomes in a certain direction. But for this example, I'm going to go ahead and do a two-sided test so that we can see how these work. I'm going to use the data that I've already shown you, and there were only 12 values, so let's go ahead and set alpha at 0.10. Although the industry standard is 0.05, it seems reasonable to me that if we're doing a study in which we have a limited number of observations, perhaps because we're dealing with a limited population, or we're doing a study in which it's hard to recruit participants, a type 1 error rate of 0.10, meaning confidence of 90%, seems quite reasonable to me. Here are our 12 values. I have kept them as an ordered list, as we saw before, from 96 to 115, and we already calculated the sample median to be 108. Here are the adjusted observations. That is, I have taken the null hypothesized value of 100 and subtracted that from each of these observations. This yields 10 positive scores. Here are the values of a binomial probability distribution with the possible number of positive signs ranging from 0, no positive signs, up to 12, all the observations are positive. As always, we should build the critical values, starting with the values that we would least expect to see if the null hypothesis is true. If our null hypothesis is true, the expectation of what we would get most of the time is half positive, half negative. For n equals 12, that means 6 of each. So the values that are furthest from the null hypothesis in terms of the number of signs are 12 and 0. Note that the cumulative probability to 0 is 0.00. Now it's not really. That would imply that there's no chance of getting 0 plus signs, and there is a chance of it. However, it's such a small number that when I round it for this table, the best rounding was to put this at 0, and similarly for 1. So we're going to work our way now from the most extreme values of 12 and 0 up to 11 and 1. Notice the cumulative probability still has not registered on our meter. Now let's move up to 10 and 2. Now I see that the cumulative probability up to 2, that means 0, 1, and 2, is 0.02. Therefore, given the symmetry of this distribution, because it's based upon the probability of positive signs being 0.5, I know that the cumulative probability from the lower tail up is the same as the cumulative probability from the upper tail down, so I can take this 0.02 and multiply it by 2 to give me 0.04. So far, I'm still under my alpha of 0.10, and I have in the rejection region 0, 1, 2, 10, 11, and 12. What about 9 and 3? Well, now if I go to 9 and 3, we see what happens. The cumulative probability from 0 through 3 is 0.07. Therefore, for 9 through 12, it is also 0.07, and now I'm up to 0.14, which is over 0.10. So my rejection region are plus signs of 0, 1, and 2, or 10, 11, and 12. I got 10, so therefore I can reject the null hypothesis, and my p-value is 0.02 times 2, or 0.04. We can conclude that the population median is not 100. Something interesting to note is that our alpha prime here, that is our actual type 1 error rate, was 0.04, even though we had set a nominal error rate at 0.10. In other words, if I had set my nominal error rate at 0.05, because of the small number of observations I have, 12, and this particular configuration, I would have still rejected the null hypothesis if I had set alpha to 0.05. An unethical researcher might be tempted to write up their research report as though they had set alpha at 0.05 all along, but you're not unethical, you know better than that, and you're going to write it up that you conducted this test with alpha equals 0.10, because that is what you did. It just turned out that the actual type 1 error rate is 0.04, and there is no problem in saying you set a nominal type 1 error rate at 0.10, but the actual type 1 error rate is 0.04. That is true, that is above board, and you can surely report that. What about a confidence interval about the median? We test all possible null hypotheses and put all retained hypotheses in the confidence interval. So our null hypothesis here now is that theta equals theta sub 0, where theta sub 0 can be anything. Once we set alpha, this will yield at least a 100 times 1 minus alpha % confidence interval. Let's construct the confidence interval using the same data. Here are the original observations. Here are the adjusted observations, and here again are the values in the binomial probability distribution. Now, the key to constructing this confidence interval is to recognize that we're going to put all retained hypotheses in the confidence interval. A moment ago, we just conducted a hypothesis test about 100, and that's how we derived these adjusted observations. When we did that, we were able to reject the null hypothesis, so we already know that 100 will not be in our confidence interval. We also discovered that the critical region was 0, 1, and 2, 10, 11, and 12. So 9 is not in the critical region. What is the smallest number that I could subtract from my original observations to end up with 9 plus signs instead of 10? You should only have to look a moment and say it would be 102. If you subtracted 102 from these observations, you would end up with 9 adjusted values that would still be positive. Therefore, 102 is going to be one boundary of our confidence interval. On the other side of the binomial distribution, we know that if we have 3 plus signs, we will not reject. What is the largest value that we can subtract from these original observations and still have 3 plus signs? That would be 111. Actually, it would be anything under 112. Even if I used 111.9, we would end up with 112, 113, and 115, resulting in adjusted scores that would be positive. We have now found the boundaries of our confidence interval. Anything between 102 and 112, when we do the adjustment, will add up with a number of plus signs that are somewhere between 3 and 9, meaning that we retain the null hypothesis. Therefore, the median in our population is between 102 and 112, and I'm at least 90% confident in that statement.